Okay, so when we're talking about trends in subsequent ionization energy, there's a few things you've got to realize. So I'm just going to take M for any like generic metal. Okay, so the first ionization energy, I'm just going to call it IE1, is going to be given by the generic expression that your metal, and it should be in the gas state, right? um, is going to form a cation, like M plus, and lose an electron. So bye-bye electron. That's your first ionization energy, okay? And then your second ionization energy, okay, would be that already positively charged metal, so a +1 cation, is then going to form a +2 cation, and by losing another electron. You could write a third ionization energy, okay? So you've got now a +2 metal, M2+, which is then going to lose an electron to form a +3 metal, and so on and so forth. Okay, so it stands to reason that each ionization energy is going to cost more because removing an electron from something that is neutral is going to cost energy, but it's not going to cost anywhere near as much energy as trying to remove something that is neutral from a positively charged species. Okay, think about it. Opposites attract in terms of charge. So if you've got a +1 cation and you're trying to remove an electron from it, it's going to cost you more. So you will see that ionization energy 1 is always the smallest. Then ionization energy 2 will be a bit bigger, sometimes as much as like twice as much. And then ionization energy 3 will be bigger than that, etc. But if you imagine something like, I don't know, let's pick on magnesium, because it's right there, right? So ionization energy 1 for magnesium, let's say it's like 500, right? Ionization energy 2 for magnesium would be like maybe double that, like 1,000. But ionization energy 3 means we got to lose one of these core electrons, okay? So think about the electronic configuration of magnesium, right? It's going to be the argon configuration, sorry, not argon, neon configuration, and then it's this key keeps getting stuck. Yes, I did spill coffee on my computer. So it's going to be 3s2 will be for magnesium, and then magnesium plus will be 3s1, right? Oh, I'm scared to touch the key. Yeah. Oh, there we go. Will be 3s1. Magnesium 2 plus will just be the neon configuration. So if we want to form magnesium 3 plus, if I could pick the right button, we're then going to have to dig in to this neon configuration to end up with like helium 3, no, 1, 2, S2, 2p5. Energetically, how much do you think it's going to cost to take one of those p electrons, the 2p electrons, out to make magnesium 3 plus? It's going to be huge, right? So for magnesium, you're going to see a huge jump, right? Ionization energy 3 for magnesium, ionization energy 3 is going to be so much bigger than ionization energy 2, which is going to be a bit bigger than ionization energy 1, for example. Okay, so when you see a huge jump in ionization energies like this between 2 and 3, I know that is a +2 cation. So if we look at this problem here, I can see that there is a little jump, a little jump, a little jump, and a big jump, right? So these are the little jumps. That's telling me it's a +4 cation, okay? Got to be +4 because this ionization energy 5 is removing a core electron. And we're told the elements in period 3, okay, so period 3, 1, 2, 3 is this one. So a +4 cation from period 3, 1, 2, 3, 4, just count +4. I know that that is going to be silicon is the element, okay? Has to be, okay? That's the only option. All right, so let me just scrub out these other ones. Okay, so let's do another one just to make sure we're cool with this. See if it's something a bit different. Show me another one. That's not +4, preferably. All right. So this one, I see there's a big jump between ionization energy 2 and ionization energy 3. Right here. Look, these ones are lower, and then we got huge jump. So that's telling me to get to ionization energy 3 is going to be removing a core electron. We're in period 6. So let's look at period 6 and see what element it is. No. I don't want to do this one. 1, 2, 3, 4, 5, 6. 6s1, 6s2. I know that that has to be barium. Okay, so barium is the element because first ionization energy, corresponds to removing this 6s2 electron. Second ionization energy is removing a 6s1 electron, but that third ionization energy is trying to remove that 5p6 electron, and that ain't happening. So that is barium. Gotta be. All right, so hopefully that's helpful for you guys. Look for the jump.